Yeah, read the activity 2.
Sir, wait. Activity 2. Take a slinky. Ask your friend to hold one end. You hold the other one and the other end. Now stretch the slinky as shown in figure 16.4. Then give it a sharp push towards your friend. What do you notice? If you move your hand pushing and pulling this slinky alternatively, what will you observe? If you mark a dot on the slinky, you will observe that the dot on the slinky will move back and forth parallel to each other to the direction of the propagation of the disturbance.
So you already understand what is called longitudinal wave, right? It
Yes,
is
sir.
back and forth vibration of the particles, right?
Yes, sir.
Yeah, continue.
Okay. The regions where the coils become closer are called compressions, C, and the regions where the coils are further apart are called refractions, R. As we already know, sound propagation in the medium as a series of compression and rarefaction. Now we can compare the propagation of disturbance in a slinky with the sound propagation in the medium. These waves are called longitudinal waves. In these waves, the individual particles of the medium move in a direction parallel to the direction of propagation of the disturbance. The particles do not move from one place to another, but they simply oscillate back and forth about their position of rest. This is exactly how a sound wave propagates. Hence, sound waves are longitudinal waves. Speed
Okay,
of
wait,
sound is.
wait. Now, you wrote that heading, right?
Yes, sir.
Sound is longitudinal waves. Now you write this bold one, right? You say sound propagates in the medium as a series of compressions and rarefactions. Okay,
Yes, sir.
write this, the bold one. Yeah,
Sir,
Monica.
from the regions, sir.
Yeah, I'm saying this one, the bold one only.
Oh, okay, sir.
Excuse me. Yeah, Monica. Hello, Monica.
Yes, sir.
So you write the sound. Sound is longitudinal wave. You give a heading, then you write this. Sound propagates in the medium as a series of compressions and rarefactions. Once you are done with this writing, then you write this bold also. Mahi, the
Okay, sir.
particles do not move from one place to another, but they simply oscillate back and forth about their position of rest. This one you write. In our topic 13, you got this idea also, right? That particles do not move, the energy only transfer, right? Particle,
Yeah,
the
yes, sir.
wave transfer energy without transferring matter. That one you got in topic 13. So the same idea we are having here. The particles do not move from one place to another, but they simply oscillate back and forth about their position of rest. So once you are done with writing, then you tell me you are done. These two bolts only. This sound propagates in the medium as a series of compressions and rarefactions. When the particles do not move from one place to another, but they simply oscillate back and forth about their position of rest. Are you done, both of you?
Yes, sir, I'm done.
Yeah, Monica also done, right?
Yes, sir.
Okay, now you write this heading: speed of sound in different medium. Speed of sound in different medium. It is a uh, a very common question coming in O-level exams, and in most of the cases, students get confused with this. Okay, so here you will learn about the fact that sound travels most in the solid medium and sound travels least the speed of sound is least in the air. So that one we are going to understand from here. So Monica, you read here. From here, read. Sound propagates.
Sound propagates through a medium at a finite speed. The sound of a thunder is heard a little later than the flash of light is seen. So we can make out that sound travels with a speed which is much less than the speed of light. The speed of light The speed of sound depends on the properties of the medium through which it travels. The speed of sound decreases when we go from solid to gaseous state. In any medium, as we increase the temperature, the speed of sound increases. For example, the speed of sound in different medium at 25 degrees Celsius in air, it is 346 meter per second. Water C 1500 water distance 98 meter per second. Nickel 6040 meter per second. Steel 9000 no 5960 meter per second. Iron 5980 meter second. Denser the molecules, more the vibrations. Higher the speed of sound in the medium.
So you have written this heading, right? Speed of sound in different medium. Have you written?
Yes, sir.
And already you understood where the sound is most and why it is most, right? So speed of
Yes,
sound
sir.
depends on the medium's density. You know that sound travels by the vibration of molecules, right? So if you think of the structure of solid, in solid the molecules are most closest, right? Isn't it?
Yes, sir.
And that's why they can transfer energy to the next molecule easily, the sound energy. That's why sound is uh, fastest in the solids. So you write here this bold one you write, these are the molecules, more the vibrations, higher the speed of sound in the medium. This bold one you write, then you write speed of sound in air, speed of sound in water, speed of sound in iron. These three you write only.
Sir, can you say it again?
Yeah, speed of
I got confused.
yeah, you you see which one you are confused? The one I told, which one you have to write? That one or the whole thing you are confused?
Like after the bold.
Yeah, after the bold is written, right?
Yes, sir.
So after writing the bold, then you write the speed of sound in air. It is 346 meter per second. The speed of sound in water, that is 1530 meter per second. There is speed of sound in iron. These three only you write, okay?
Okay, sir.
Other things you do not need to write. Just remember the order, how it is changing. In air, it's only 346. In water, it is around 1500, right?
Yes, sir.
And in iron, it is around 6000 meter per second. So the order at least you can remember, okay?
Okay,
Because
sir.
in O level questions, they are giving this one that what is the typical speed of sound in water or in air or in solid. That time you can mention this, right? You just remember this. Also in MCQ it comes. So done, right? This part is also done.
Sir, yes, sir, done.
Monica, you are also done, right? Monica,
Yes, sir.
so you write this heading. Sound requires a medium to travel. Sound requires a medium to travel. So you might have this experiment before also, right? You are familiar with this experiment. This is an experiment which one let us understand that sound requires a medium to travel. So, Mahi, please read it, huh?
Okay, sir. Sound requires a medium to travel. Sound is a mechanical wave and needs a material medium like air, water, steel, etc. for its propagation. It cannot travel through vacuum.
Yeah, Monica, you continue, huh? Hello, Monica.
Sir, from the first,
Yeah, from here, sound.
sound is a mechanical wave and needs a material medium like air, water, steel, etc. for its propagation. It cannot travel through vacuum, which can be demonstrated by the following experiment.
Yes, you see this arrangement here. There is one uh, glass jar. This is called bell jar, and there is one electric bell inside it, and we have here vacuum pump to take the air out from inside the bell jar. Okay, now read from here, please. Take an electric bell. Yeah, Monica, read from here. Take an electric bell.
Take an electric bell and an airtight glass bell jar. The electric bell is suspended inside.
Mm-hmm. Yeah, read, please. Hello.
The electric bell is suspended inside the airtight bell jar. The bell jar is connected to a vacuum pump, as shown in Figure 16.5. If you press the switch, you will be able to hear the bell. Now start the vacuum pump. When the air in the jar is pumped out gradually, the sound becomes fainter, although the same current is passing through the bell. After some time, when less air is left inside the bell jar, you will hear a very feeble sound. What will happen if the air is removed completely? Will you still be able to hear the sound of the bell?
Hmm. So the answer is no. Okay. If all the air is taken out, we will hear no sound because no medium is available inside, right? Have you
Yes, sir.
understood? So
Yes, sir.
you wrote this heading. You got sound requires a medium to travel. Then you write Belger experiment. Huh? Belger experiment and draw this diagram. You draw this glass jar. Then electric connection here. You give and the bell inside it. And level here vacuum pump. Huh? Air is taken out by the vacuum pump.
Sir, we have to write the full paragraph.
No, no, not the full paragraph. I will tell you. Just draw this diagram because this diagram will help you to understand everything, right? So we will not go for all the things writing. Only will write very little to understand it. You you draw this and you write here the figure caption Belger experiment. Hmm. Are you done with drawing?
Mm, Labeling them.
Mhm.
Done, sir.
Very good. So you write here, if the air is inside, that time we hear the rings of the bell. But if the air is taken out completely, then we hear no sound.
If the air is inside,
Inside the jar, glass jar, then we hear the sound of bell, uh, sound of the bell. And if the air is taken out, then we hear no sound, even though bell is ringing. Done?
yes, sir.
Okay, very good. So, bell jar experiment you understood, right?
Yes, sir.
Then you write range of audible sound and ultrasound.
Okay.
Okay, then you read the human ear. Read please the human ear from here.
The human ear responds to sounds with frequency in the range from 20 hertz to 20,000 hertz. This is called the audible range of the human ear. Examples of vibrating sources that produce sound in the audible range of frequencies are drums, guitar strings, tuning forks, human vocal cords, and diaphragms of loudspeakers. Inaudible sound waves whose frequencies are less than 20 Hz are in the infrasonic range. Sources of infrasonic waves include earthquakes, volcanoes, and waves produced by vibrating heavy machinery. The hearing ranges of elephants and whales extend into the infrasonic region. Frequencies above 20,000 Hz are in the ultrasonic range. The audible range of dogs, cats, mice, etc. extends into ultrasound frequencies. They can hear very high frequencies that humans cannot. Ultrasound is the sound with frequencies higher than 20 Hz.
Okay, from here you will write from here the human ear till human ear. Okay, so understand what I said.
Yes, sir.
From here to here, then here to here. Okay.
Okay, sir. Done, sir.
Okay, today we are done till here, right?
Yes, sir.
In our next class, we'll continue, okay? After this, and you do the pending works. I'm not giving any work from sound now. Just you have the printout of the worksheet. In next class, we will have some discussion on worksheet also, okay? And now I'm not giving any more homework from sound as we have some pending works to receive from you, right? So you send me those
Yes,
on
sir.
topic 13, topic 15, the pending works you have, you send me them, okay? Allah Hafiz, huh? Bye bye.
Allah Hafiz. Bye-bye.